Hi, my name is Felix Terhag, and I present the poster Post-hoc Uncertainty Estimates to Deterministic Machine Learning Models for Heart MRIs. I'm a doctoral student at the German Aerospace Center in the RWTH Aachen, and this is joint work with my colleagues from the German Aerospace Center, Philipp Neskes and Achim Basermann, and Raoul Tempone from the RWTH Aachen and the KAUST University. I want to start with the motivation for this work. So the volume of the left ventricle is a very important cardiovascular parameter. It is used to assess the state of the heart and diagnose many different pathologies. So the gold standard for obtaining this parameter is usually obtaining an MRI image of the heart. So an MRI image is pretty much just a 3D image of the heart. So we go through the heart to several slices and letting an expert segment each slice and the left ventricle in each slice. But this procedure is, of course, quite costly. Fortunately, modern machine learning models like unit structures have improved segmentation, automatic segmentation drastically, but they lack a proper notion of the uncertainty attached to it. And uncertainty estimation is, of course, very crucial in critical applications, such as medical diagnosis. And this is where we wanted to try to help, and we wanted to add uncertainty estimates to the deterministic predictions of the machine learning models, and we want to develop a method which is agnostic to the prediction technology, so that if we come up with a better segmentation algorithm, we can still use our method on top of it. So I will briefly go over the method. We start with the segmentations of the machine learning algorithm. We use a pre-trained NNU net for this. And then for every slice, we extract the volume, which is the same as the segmented volume of the left ventricle, and extract it for every slice. And so we can go through the depth of the heart and have a volume for every slice. And the first and last two slices are difficult to predict because we can imagine they cut through the wall of the heart, and this means that we can have quite drastic errors there. So we chose to model this independently of the rest with a specific jump distribution. The intermediate slices are a lot nicer, let's say. So we can model this with an SDE, and we use the depth of the heart as a fake time here. And then we can repeat the simulation of the jumps in the beginning and the intermediate SDE several times, and we get several trajectories. And then we can integrate over each of the trajectories to get a volume prediction, and each trajectory gets a single volume prediction. So we get several volume predictions and use some kind of density estimate for the final density of the predicted volume. So now we come to the results. First of all, we see that our method matches the error in the data quite well. So here on the left side, we see the error in the hearts over the full data sets of almost 200 hearts in the blue. And in green, we can see our simulation. So for each of the hearts, we evaluated several trajectories and plotted this on top. And we then can see the error range and the predicted uncertainty range align very well. We can also see that the data is shifted to the right slightly. This is due to the fact that our underlying machine learning model has a slight bias, but our method does not want to improve the prediction. It only wants to add some notion of uncertainty to it. So if we wanted to correct this bias, we would need to correct it in the machine learning model. Here on the right, we can see the normalized volume of the edge slices, because those are particularly hard. And we can see in the data in blue that we find some multimodal distribution here. And the jump distribution we specifically designed for this also shows this same specifications. So furthermore, we wanted to test the stability of the method because we wanted our method to be robust to different subsets of the data so that we can use our method also on quite small data sets. The idea behind this is when we have a medical center and we don't have enough labeled data to retrain a neural network, which requires quite some data, we can still use a pre-trained net on other data sets and only calibrate the uncertainty on our data set. So to test this, we divided the full data set into 9 subsets, and with always 3 being disjoint. And we also tested flipping each of the hearts. So we can, usually in SDEs, we have this time component where we have this predetermined direction, but we can go through the heart from the basal to the apical sections or the other way around just as well. So we also used the flipped or reverse data set and divided it into 9 subsets as well. And for each of those subsets, we evaluated the SDE parameters, and we can see that all of those lie in roughly the same area, and plotting this on the likelihood of the full standard data set, we can see that all of those parameters also lie in an area where the likelihood on the full data set is very high. And lastly, we can use our method for different data regimes. So we have quite a diverse data set. That means that we have different pathologies in the data. And this is why we have quite a wide range of heart volumes. So we decided to bin the hearts by predicted volume. Here on the left side into 8 bins and on the right side into 16 bins. And we can see that the fitted parameters for each bin show a quite clear trend. For small hearts, we have a quite large alpha times theta 0, and alpha times theta 0 is responsible for the variability in our predictions. So this means that for small hearts, we get a larger uncertainty than for large hearts. And this also allows us to use this method and adapt it for different volumes. So we could use different parameters for smaller hearts than we use for larger hearts. And looking at those 16 bins, this is also quite reassuring that this method is in fact quite robust, because dividing the data set into 16 bins leads to very small bins of 12 to 13 samples, and still we can see this consistent trend we also saw with the larger bins. So to summarize, our method adds uncertainty estimates to deterministic machine learning models, and it enhances the robustness and generalizability of the automated segmentations. This means that we are generalizable. This method is generalizable because it is agnostic to the machine learning model, and also we can use it on a quite diverse data set and adapt the method accordingly with this binning approach, for example. So thank you very much for your attention. Bye.